Welcome back. The purpose of this video is to discuss ordinary least squares, or OLS, estimates for simple linear regression. So back when in my video on what is simple linear regression, I went over this slide with you, which was all the properties of how we get the estimates from least squares. So the first thing I did was I just gave you the estimates, gave you the standard error, and then on the next page, I did things like state some theorems that, here's how we can find the standard errors of our estimates. Here are some other properties that that they're unbiased and that they're normally distributed. And we used these properties in developing hypothesis tests and confidence intervals for our regression coefficients. I didn't really justify any of these results, and so I'd like to do that in this video. Now, a couple things before we get into this. Number one is ordinary least squares is one of the major methods of estimation. So in some earlier videos, I talked about the method of moments method and the maximum likelihood method. Ordinary least squares is up there with those two methods, and it's one of the most commonly used objective functions or estimation methods in machine learning. So you really need to understand this. Another preface remark about this video is that there's another video on my website that does all of this for multiple linear regression. So multiple linear regression is where you have more than one predictor. Simple linear regression is where you have only one predictor. I have to say the algebra and everything is much simpler when we talk about multiple regression than for simple linear regression. But since this is not, we're not covering multiple regression in this class, I feel obligated to take us through these main properties in the case of simple linear regression. This follows a long tradition of statistics and regression textbooks that do basically the same thing. They present least squares theory in simple linear regression chapters, and then they go on and present it again in the multiple regression chapter. And the reason they do that twice is, hopefully it sticks after you've seen it two times. All right, so the goals for today, I've just kind of summarized here, and we're going to keep track of them. I want to derive the OLS estimates. I want to establish their properties. And what do I mean by their properties? Well, that they're normal, they're unbiased. We need to know their variances in order to find confidence intervals and do hypothesis tests. And then the last thing I'm going to just discuss a bit is their blueness. So blueness relates to a concept that we discussed way back in, I don't know, week 3 or 4, where we were discussing how a desirable property for estimates is for them to have low variance. And so what we'll see is that these OLS estimates are the best linear unbiased estimators, meaning they satisfy a version of that MVUE, so minimum variance unbiased estimate concept that we discussed way back in chapter 4. All right, so let's get to this. And I'm going to state the problem. What I want to avoid is losing the forest from the trees. So there's a lot of details that we have to worry about today, and so don't lose the forest from the trees. Keep the big ideas in mind. So I am going to change our notation slightly. So here is my model. We're going to assume that each y sub I is equal to alpha plus beta x sub I plus some epsilon sub i's. And so I'm going to change our notation slightly to avoid going crazy with subscripts to alpha and beta. We've been calling this beta naught and beta 1. I'm going to call it alpha and beta so I don't have to worry about the subscripts here. Now I've made some very specific assumptions about these errors. So we've assumed that our errors all have mean 0. The errors have variance sigma squared, and that sigma squared does not depend on the observation number. So that sigma squared does not have a subscript. That's the assumption of homoscedasticity. So I've got constant error variance over all observations. E sub I are independent of one another. So one EI is independent of another one. And then there's another assumption that we sometimes use, but we don't really need it for OLS. And that is that EI is normal, or R normal. We could say R if you want, be consistent with what I said earlier. And so as I say, this is going to be important for us to do confidence intervals and hypothesis tests. Were we to do maximum likelihood estimation, we would need this, but we really don't need it for OLS. All right, I'm just going to derive a couple quick properties. So the expected value of a random variable y is going to be the expected value of alpha plus beta x sub I plus e sub I. And so what I want you to notice is that this is simply equal to alpha plus beta x sub I. And you can think of plus 0 if you like, because the mean of these errors is 0. So often we'll need the mean of this, and we just found it. Likewise, the variance of y sub I is equal to the following. So it's going to be the variance of alpha plus beta x sub I plus our errors. Now, make that an epsilon, not an e. Think of this as a constant. Alpha is a constant, beta is a constant, so is x sub I. And so if you remember, the variance of ax plus b is just a squared times the variance of x, so that the constant goes away. So this whole thing goes away. So this is just the variance of my errors, which I've assumed to be sigma squared. So these are two things that we're going to need later on, but I just thought I would derive them now. So what is least squares? So what least squares says is this. We're going to choose our estimate of the slope and intercept to minimize this least squares criterion. So let me write that down. The OLS criterion is pick A and B. So A is going to be my estimate of alpha, B is going to be my estimate of beta, to minimize, so minimize A comma B. The sum I equals 1 to n y sub I minus, well, I'm going to drop in my predicted values. So this is going to be A minus B x sub I squared. Now this has a special name. We've been calling it the sum of squared errors. Sometimes this will be called the residual sum of squares. So I'm using SSE in this class, but in my, I think when I teach from the other book, I call it RSS. All right, so how do we minimize this? Well, what we do is we take the first partial derivative with respect to the two parameters that I'm trying to estimate. So let's do that. What is the partial of this SSE with respect to, let's start with alpha, A. And so if I take the derivative of this, I can use my product rule. So this is going to be the sum of, well, 2 times y sub I minus A minus B x sub I. Now I have to take the derivative of the base. I'm using the chain rule. So what is the derivative of negative A with respect to A? It's just minus 1. So that's going to be my first partial derivative, and we're going to set this equal to 0. Then we have to go find the second, the derivative with respect to B, and this is going to be something really similar. So it's going to be the sum, and it's going to be the same thing, y sub I minus A minus B x sub I. Now I have to take the derivative of this base with respect to B, which is negative x sub I. So negative x sub I, that's an I there, times 2 of this. And this is equal to 0. So these are called the normal equations. So they are the normal equations. And what may not be obvious from the way I've written it here, but it's important to note, is that I have a system of 2 equations and 2 unknowns, and it's a linear system of equations. Now, I'm going to do a little bit of rewriting on this. So let's just take this first equation. So I'm just going to draw a little arrow down here. And actually, before I do that, I want to just mention something that ought to be obvious, but may not be. So remember what x bar is. So x bar is just 1 over n times the sum of xi's. But we can do something extremely simple, multiply both sides by n, and make a conclusion that the sum of xi is just n times x bar. So there's nothing that complicated about this, but this is a result that we're going to use many, many times in this video, and I just wanted to remind you of this. So I can do some rearranging on this, and what I really have here is -2 times the sum of my yi's, and I'm going to move these other sums to the other side. So really I have -2 times the sum of a. This would be I equals 1 to n if you want to keep track of your subscripts. I'm also going to have a -2 times the sum of b xi. Now, what I really have on this side, the -2's all go away. So the -2, that becomes a plus then once I cross -2 out in all places. We can think of this as y bar, so n times y bar, using this result that I just gave us. And then we have n times a, as I have n copies of that a. And then what do I have here? Well, what I have here is b times nx bar. So nx bar. And so my n's all cross out, and I'm just left with y bar is equal to a plus b times x bar. And so I have one equation now with my 2 unknowns. So just as a reminder, here are my 2 unknowns. Well, let's go rearrange this other, the other partial derivative, doing something very similar to this. So, what you could do is write this as -2. So I'm looking up here at this this expression. So -2 times the sum of xi times yi. And then what I really have here is, well, -2 times a minus a is going to be plus 2. I'm going to pull this out, a times the sum of xi. And then what I have in this last term is going to be 2 times b times the sum of xi squared. And this is all equal to 0. So I can cross out my 2's. 2's go away, and then I can move this over to the other side. So we end up with this. The sum of xi times yi is equal to, all right, now remember what this is. This is going to be a times nx bar. And then what I have here, I can't do anything with right now. This is just going to be the sum of xi squared. So let me just put a little box around these. Here are my normal equations in a modified form. So one way that I could solve this is to substitute in my, my first equation into the second equation. Before I do that, though, I need to establish another symbol that's going to help me streamline the algebra. And so this is a symbol that is used pretty universally in statistics books. It's S sub xx. And so S sub xx is going to be this quantity. So sum I equals 1 to n of xi minus the mean squared. Now, I need a little rewrite on this. So this is the definition of the term. What I'll do is I'll just simply expand the squares here. So we can think of this as the sum of xi squared minus, well, 2x bar xi plus x bar squared. And so let's just go do a little bit of rearranging on this. I end up with the sum of xi squared, if I start distributing the sum sign over this. And what I have here is minus 2x bar, so there are no subscripts in there, times the sum of xi. And then this last term is I'm adding up x bar squared n times. So we can think of this as simply n times x bar squared. Now, what is this thing right here? Well, this is just n x bar, right? Going back to this this result that I said we were going to use a lot of times today. And so clearly what I have here is 2n times x bar squared, and then I have n x bar squared. So this works out to be the sum of xi squared minus, I got minus 2 of these, I got plus 1 of that, so minus x bar squared. So we're going to end up using that quite a bit. I'm going to define another new symbol that we're going to use to simplify our algebra. Now, if your head is already spinning from all these equations, you're going to love the matrix approach, because all of this just gets stored in a matrix, and your life is much easier. So what is this thing, Sxy? Well, this is going to be the sum, I equals 1 to n, of xi minus x bar times y sub I minus y bar. And so this is going to be the sum of the centered products of the two variables. Now, I'm not going to do the steps. Maybe I'll leave that as an exercise, but it turns out that you can rewrite this as follows. This is just the sum of xi, yi, and it's going to be minus n times x bar times y bar. So I'll leave that as an exercise. It's pretty straightforward. You just do what I was doing up here to get that result. All right. So now what I want to do is go substitute this first equation into the second. So just notice that A is going to be B, y bar minus bx bar. So if I just move the bx bar over to the other side, I get that. All right, so then what I have here is the sum of xi, yi. So I'm just going to draw a little arrow saying I'm going to substitute in what I had in my first equation for what I have in that second equation. So this is going to be y bar minus b x bar. So that's my A, times n times x bar, plus, well, b times the sum of my xi squareds. So now I have one equation in one unknown, and I just need to solve this thing. So I'll do the obvious thing and start distributing this. So we have n x bar y bar minus, well, what I have here is going to be b times n times x bar squared. And what I have here is b times the sum of xi squared. Nothing there changes. So what I'll now do is move this term over to the other side. So let me write it out. This is the sum of xi, yi minus n times x bar, y bar. Well, I think we've seen that. That is this quantity up here. So this we're going to have as just Sxy. That's very convenient for us. And let me just change the order of these terms and factor out the b. So I have b times the sum of xi squared minus n x bar squared. Well, we just found that over here, this is simply SXX. And so this equation, after I've made these strategic substitutions, becomes extremely simple. So my B, my OLS estimate of B, is simply going to be SXY all over SXX. And that's that's fairly easy to compute with the data that I have. So I can easily go evaluate this expression, evaluate this expression. If I do so, I know B. Once I know B, I can go substitute that into this equation to find my A again. So that's how I find my OLS solution. Well, before I move on, I want to just find some equivalent ways to write this that will help us a little bit. So I hate to do this, but I'm going to write out what this is. So xi minus x bar times yi minus y bar. And then in the denominator, we have the sum of xi minus x bar squared. And what this should look like to you is the correlation coefficient, but we got to do a little bit of work to it first. So the correlation coefficient is what's in the numerator divided by the square root of this thing times the square root of the variance of my y's. All right, so I'm going to kind of leave this as an exercise. This is going to be r times the standard deviation of my y's over the standard deviation of the x's. So if you multiply this by a version of 1, you'll get this. Where what is s sub y? That is 1 over n minus 1 sum yi minus y bar squared. And what is s sub x? Well, it's the sample standard deviation of x, which would be 1 over n minus 1 sum xi minus x bar squared. I ran out of space here, but that's the sample standard deviation of x, sample standard deviation of y. And so that's the way I wrote it in the course packet. So we've now established our least squares estimates. So I'm going to go put a little check mark next to that first one. So we've derived the estimates as promised. I'd now like to show the normality of these estimates. So the way I'm going to do this is to rewrite the second expression that I had for B. And so I'm going to take this piece right here, and I'm going to write this as, I'm going to give it a new name. We're going to call this C sub I. So let's just begin anew here. C sub I is going to be x sub I minus x bar divided by this thing in the denominator, which is SXX. So what I'd like you to notice is that my B, following from this, is equal to the sum of this big messy thing that I've called C sub I. So C sub I is just a constant, times y sub I minus y bar. Now, let's go distribute the C and the sum sign. So what I end up with is this is going to be the sum of Ci yi minus, well, y bar I can pull out since there are no subscripts there, times the sum of Ci. Now, what I'm going to show you in a second is that this is equal to 0. So this whole thing is equal to the sum of Ci times yi. Now, this is really important because what I have here is a linear combination of normal random variables. So this is where I'm going to use my normality. So when I stated the problem back here, I said the errors are normal. Therefore, y is just a linear combination of this normal error. Now I'm going to take a linear combination of a bunch of normal things. Therefore, B is also going to be normal since it's a linear combination of normal things. We can say the same thing about our estimate of the intercept. So I have a normal thing, I have another normal thing, and I have a constant here. Therefore, A is also normal. So all of this is established provided I can show that the sum of the CIs equals 0. So let's go see if we can do that. The sum of the CIs will equal the sum of, well, xi minus x bar all over sxx. So I'm going to pull SSX out. And then what do we have in here? Well, we have the sum of xi minus, I have the sum of x bar. And this sum ranges from 1 to n. So this is really just n x bar. Well, what is the sum of xi? That's also n x bar. So this thing is 0. And we've established this little thing we needed to have this alternate form, making it obvious that B is a linear combination of normal random variables and itself is normal. So what I'd like to do is put a little check mark next to that objective. Well, let's move on through our list here. I'd like to be able to show that my estimates are unbiased. And so let's go do this. What is the expected value of B? Well, let's use this last representation that I had. So the expected value of B is equal to the expected value of the sum of Ci, Yi. All right, well, remember I can pull the sum out and the constants out. So the expectation of a sum is the sum of the expectations here. So this is going to be the sum of Ci times the expected value of Y sub I. Now, what was the expected value of Y sub I? Well, we already figured that out, and it was up here. So I'm going to go drop that in. So let me just refresh your memory. This is alpha plus beta x sub I. So I'm going to go drop that in. We are left with the sum of C sub I times alpha plus beta x sub I. And what I have here is alpha times the sum of C sub I. And then I'm just distributing this. This is going to be beta times the sum of C sub I, x sub I. Now, what we know is that this thing is 0. And the reason that's 0 is because we just showed that. What I haven't shown is this thing. This thing turns out to be 1. So I'm going to make this a homework problem, but let's just say show. So you have to show that the sum of C sub I, xi is equal to 1. It's very similar. You just drop in the definition and note a few things and you get that result. All right, so we have now shown that B is unbiased. What about A? So what is the expected value of my A estimate? Well, remember what A is. It's the expected value of Y bar minus B times X bar. So what we have to do now is a little bit of messy work here. This is going to be the expected value of, what is Y bar? So this is going to be 1 over n times the sum of, well, I equals 1 to n. What is my Y sub I? It's going to be alpha plus beta x sub I plus E sub I. And then what I have over here is minus B times x bar. So I'm going to pull out the 1 over n. I'm going to pull out the sum sign. And what we have here is the expected value of all this is just alpha plus beta x sub I. And if I do the same thing here, the expected value of b is beta. So this is going to be x bar times beta. So let's go do a little bit more work on this. I have 1 over n times the sum of alphas. So this is just going to be alpha. If I add up alpha n times and divide by n, I get alpha. And what do I get here? Well, I'm going to have 1 over n times beta times the sum of xi. And we remember this is equal to n times x bar. And this is, well, x bar times beta. So this n crosses out with this n. We have beta times x bar minus x bar times beta. So this whole thing is 0. So I'm left with alpha. And so what I claim is that my estimates are unbiased. So the next thing that I want to do is establish the variance of these estimates. So why do we care about the variance of the estimates? We need the variance in order to substitute in appropriate values to compute the standard errors. So let's go do that. What is the variance of B? Well, the variance of B is going to be the variance of the sum Ci times y sub I. Where did I get that? Well, that was my this convenient form for B that I've derived. All right. So what I can do with this, since my yi's are independent of one another, the variance of this sum is just the sum of the variances. These c's are constants, so they're going to come out, and I'm left with this. This is going to be the sum of Ci times the variance of yi. Don't forget that Ci should be squared. All right. And what is this quantity? Well, we found this at the very beginning to be sigma squared. So let me just refresh your memory going back to the beginning of this lecture. This is C sub I, sigma squared. Now, this is equal to, I'm going to pull this out. So sigma squared times the sum of Ci squareds. It turns out this is equal to 1 over Sxx. And so I'm going to leave that as another exercise. So the answer is this is sigma squared over Sxx, where you need to show that the sum of my Ci squareds is equal to 1 over Sxx. All right, the last result is to find the variance of my A term. So what is the variance of A? My intercept. This is going to be the variance of y bar minus b times x bar. Now, the first thing to note is that I've assumed these x's are known and they're not random quantities. So the x's are not random. All right, so what that means is that x bar is a constant. Now, this is equal to the variance of x bar plus, that's a constant, so we can just bring it out, x bar squared times the variance of b. And then what I'm going to have is minus 2 times b, no, sorry, 2 times x bar times the covariance of y bar and b. So I'm going to leave as another exercise to show that y bar and b have a covariance of 0. All right, so that's an exercise. What do we have here? Well, the variance of a sample mean is just sigma squared over n. And what I have here is x bar squared. What's the variance of b? We just found that to be sigma squared all over SXX. So we could factor out the sigma squared if we like. So this is going to be sigma squared times 1 over n plus x bar squared all over SXX. And so this is the formula that we would use to find the standard error of the intercept if we wanted to find, for example, a confidence interval or do a hypothesis test. This would be the formula we would use to find the standard error of the slope when we do our hypothesis tests. So what I'd like to claim is that now we know their variances. Another thing that we need to know is the covariance, but we don't really use that in the basic hypothesis tests that we've been doing. So I'm not going to bother doing that, but that could be another exercise where you find the covariance between A and B. So the last thing I wanted to just mention was this issue of blueness. And I made a very rough statement in the course packet, and the result was this, that B1 has a variance that's smaller than any other linear unbiased estimator and is therefore called the blue. So B is best linear unbiased estimator. This has a very famous name. It's the Gauss-Markov theorem. I'm not going to prove that. That one's a bit more involved, but I am going to give you a homework problem that asks you to show it in a simple setting where you don't have the intercept. If you just have a slope, meaning a line through the origin, the Gauss-Markov result is much easier to understand and prove. So let me just kind of summarize again what I've done in this video. So we've now established our OLS estimates, and we've established the key properties that they're normal, so we can do hypothesis tests with them with the normal distribution or t-distribution. They're unbiased. We know their variance, so we know the standard errors, and they have this desirable property of having lower variance than any other unbiased estimator that's a linear combination of your y's.